Back in the AJCSE, we talked about things that could only be positive, like speed, and then things that could only be negative, like velocity. Well, it turned out that we were making things a little bit too simple. Really, in physics, there's two types of things. Some things have a direction, point somewhere, and some things they don't. Let me give you an example. So for example, I could say at this point here, the temperature is 25 degrees. Now in this case, it doesn't really make sense to say that it's 25 degrees this way or this way or this way or this way. This is just a number. Here the temperature is 25 degrees. We call this type of number, which is just a number, a scalar. Now think about something else. Let's say that, for example, I'm moving, and I'm telling you that my velocity is, let's say, 5 meters per second, which is very, 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 very fast. But anyway, my velocity is 5 meters per second. Now, that doesn't really give you all the information that you could have, because, see, I could be going this way or this way, but I could also be going really in any direction in this horizontal plane. So if I really want to tell you my velocity, how I'm moving, I have to tell you not only how fast I'm going, but also in which direction I'm going. Now, when this is the case, we call the number a vector. And it's not a number anymore, because you need more information than for a scalar. In a scalar, it's like 25 degrees. Okay, I give you one number, you're done. You know everything there is to know. With a vector, I give you one number, which we call the magnitude, and we'll get into that later. And you know a little bit about it, but you still don't know in which way it's pointing. Which way am I going? This way, this way, this way, this way. I need another number. Or sometimes I need several numbers to know the direction that this thing is pointing. Just to see what I mean in a little bit more detail, let's take a look at several examples and then try to decide on your own whether they're vectors or they're scalars. So for example, I'm going to talk about energy, force, acceleration, and volume. So we have energy, force, acceleration, and volume. Now, let's start with energy. Now remember that when you have energy, it means that you have the capacity to do work. And the energy just tells you how much work you can do with that energy. Of course, it doesn't tell you in which direction you can do the work or where it's going. So this should be a scalar. Now if you take a look at, for example, acceleration, and I tell you that you're accelerating at 2 meters per second squared, you may ask me, yeah, but in which direction? Am I accelerating forward? Am I accelerating backwards, to the sides, up, down? If I don't tell you more, you have no idea what's really happening. Therefore, acceleration is a vector. Force is sort of the same, right? If I'm saying I'm doing 20 meters of force, it's like, well, okay, but are you doing it forward or backwards or to the sides or what? Again, force has to be a vector. Volume, on the other hand, is a scalar because it's just a number. This bottle has a volume of 1 liter. Thinking about the direction of this liter makes no sense whatsoever. There are many ways of representing vectors. Some of them are mathematical, some of them are graphical. Today we're just going to focus on the graphical ones. A vector really is just an arrow. So, for example, this is a vector. This is a vector. This is a vector. Now, if you take a look at an arrow, there's several things about it. Well, the first thing that you can notice is that each arrow has a length. So, for example, this one is longer than this one, which is longer than this one. So the length tells us something about the vector. So, for example, if this was velocity, I would conclude that this guy is faster than this guy, because the length of this vector is bigger. Now, we normally don't call this the length. We call this the magnitude of the vector. So the length of the vector is really called the magnitude. And the reason for this is that it's really not a length at all. So for example, if my speed is 20 meters per second, that's the magnitude of the velocity vector. But it doesn't mean that this is really a length, right? It's just how much of it there is. And magnitude is a much more generic word that would work for a length, but it would work for other quantities. Some people, and me included, will sometimes call this the module of a vector. So if you hear me saying module, know that I mean just the magnitude of the vector. And then the other thing that these things have is a direction. Right? They're all pointing somewhere. This one's pointing this way, this way, this way. Now, the term direction is actually the technical term. So we say that vectors have a magnitude and a direction. We normally show this direction by showing an angle. And the angle that we usually choose is if this is in a coordinate axis. So for example, let's just say that this is y-axis and this is the x-axis. We talk about this angle here, the angle that this vector does with the x-axis. And we normally denote this angle with the Greek letter theta, which is sort of like an O, the ones that you did when you did calligraphy. So again, each vector is represented by a magnitude and a direction, and two vectors are said to be the same vector if both the magnitude and the direction are the same thing. So for example, these two vectors, even though they have roughly the same magnitude, are not the same because they're pointing in different ways, and therefore they do not represent the same physical situation. However, these two vectors are exactly the same because they have the same magnitude and direction, so they represent exactly the same physical situation. Now, just like numbers, we can also add and subtract vectors, but things are not as straightforward as with numbers. So, for example, let's just say that I want to add these two vectors, and this could represent, for example, those two people pushing in different directions. One guy is pushing this way, and one guy is pushing this way. Now, you would not expect these two guys to add up as if they were both pushing in the same direction exactly. For the same reason that if you are pushing, for example, in opposite directions, basically your forces will not add, but they will subtract from each other. So the addition of these two things should be, of course, bigger than any one of them, but it shouldn't point in this direction or this direction, and it should be a little bigger than either, but not as big as if they were both put together. Now, there is a relatively straightforward way to add vectors, and this one is called the parallelogram rule. It's relatively easy to imagine. You take one of these vectors and you move it to the tip of the other one, and it doesn't matter which one you do. So I could do this one like this, but I could also do this one like this, and I would get exactly the same result. And then I make another vector from the bottom of one to the tip of the other. The red vector is the result of adding these two vectors. As you can see, this is a little bit shorter than if I had taken this one and then put this one right after like this. And still longer than either of them. And it's still not pointing in the direction of either of them. So for example, if I show you this one, so this is the way that they used to be. So this one's sort of like in the middle. Now, this rule is called the parallelogram rule simply because it's as if I made a parallelogram. If I take this vector here and I put it here as a point line, or I take this vector here and I put it here also as a dashed line, you'll see that it makes a parallelogram. So this is why it's called the parallelogram rule. Now, we can add vectors and we can also subtract vectors graphically. Let me just show you how that's done. And there's several ways to do it. Now, when you subtract vectors, it's necessary to specify which one is being subtracted from which one. So for example, if I have the white vector and the red vector, I can say what is the result of subtracting this guy from this guy. If the question was the other way around, subtracting this guy from this guy, I would get a different result. Now, in order to subtract vectors, what I find easiest to understand is simply to think, well, subtracting is the same as adding the inverse, really. So 4 minus 2 is just saying 4 plus minus 2. So what I can do is say, well, okay, what would be the inverse of this guy? Well, I just need to make it a little bigger, so I just need to see where would it go if it was going the other way. And then I make a vector which is exactly like this one, but pointing in exactly the opposite way. So, for example, if I have a vector that points this way, I just continue it the other way with the same length, and this would be the opposite of this. And now that's it. Now the question becomes, what is the addition of this and this vector. And then this is easy to do because it's just the parallelogram rule. So I just either make a parallelogram or I move one of the two vectors. So I just take this one, and excuse my complete lack of skill, but this is really hard to do from where I'm standing. Okay, so here's my vector, and then I just need to make the resultant vector, which is this one, because remember, it goes from the bottom to the top. Done. Now, another way that people do this, which also works, is the following method. So imagine again that I have two vectors and I want to subtract them, vector number 1 and then vector number 2. Now, it turns out that if I draw a vector going from the tip of this guy to the tip of this guy, I get the subtracted vector. Let's just try. So this would be the subtracted vector, and you can see how this works, because if I took this guy and I put it over here, then my resultant vector would point somewhere here, so it would be something like this. But remember, even if the two vectors start at different points, like this one and this one, they would still have the same magnitude and the same direction. And that is the only thing that matters for vectors. If they have the same magnitude and direction, then they're the same vector. So that's all you need to know for now. Do the problems, go back to the initial questions that I asked you to check whether you knew what you were doing, and once you're done with everything, then you can move on and we can start doing some mathematics. Have fun.